This is ELEC142 problem sheet 6 on filters, and this is going to answer question 1. So here we've got a diagram of a filter with a resistor and an inductor, and you're asked to answer a series of questions about this. So figure 1 shows a passive RL filter. All of the filters we've looked at so far have been passive. This is because they've got no power supply of their own. If you build a filter with an op amp, that has a power supply to it, so that actually affects the gain, and it means that it's not passive. So passive just means that there's no additional power supply going into this. So we're asked to the following questions. So A, is the filter a low or high pass filter? B, to calculate the cutoff frequency omega naught. C, to redraw the circuit as a potential divider. D, to calculate the complex voltage transfer function H of j omega. E, to find the amplitude and phase response for the filter at low frequency where omega tends to 0. F, to do the same where omega tends to infinity, so that's high frequency. Part G, to find what the amplitude response is at the cutoff frequency where omega is equal to omega naught. And then finally H, to plot a straight line Bode plot for the filter. So let's answer the first part of this question. Is it a low pass or a high pass filter? Well, what I've done is I've used my handy filter grid that you were handed out in a lecture, and there's also a copy of this on Vital in the lecture notes section if you don't have a copy. So we're going to use this just to help make our life easier. So let's see what configuration our filter is. If we look at it, we've got the resistor at the top and the inductor on the vertical. So the resistor on the top and the inductor on the vertical. So what we can see is this is actually a high pass filter. So that's the answer, that it's a high pass filter. So what do we write? Oh yes, it's a high pass filter. Just to show you how long this question's approximately going to take, is that it takes about 2 pages of calculations, and then we've got our Bode plot. So that's about how long it took me. So you should have approximately this level of detail in your solution. I'm just going to zoom in a bit to make it easier to see. So first up, it's a high pass filter. I've redrawn this because that's the way I work. I find it more convenient to have it in front of me on the piece of paper I'm working on. Second up, part B, we're asked to calculate the cutoff frequency omega naught. And if you look at your filter grid sheet here, you can see that for any filter which is built with a resistor and an inductor, the cutoff frequency, well, that doesn't like highlighting that really, does it? Omega naught is going to be equal to the value of the resistor over the value of the inductor. So this is in ohms and this is in henries, and this cutoff frequency is going to be the same whether it's a low pass filter configuration or a high pass filter configuration. It's the positions of the resistor and the inductor, because you can see they're different in the low pass and the high pass versions, which change the behaviour, but the cutoff frequency remains the same. So using this equation, let's calculate what that is. So omega naught is equal to R over L, which is, oh, I've not got a cursor. Select tool. Yeah, that's the one. Okay, R over L, which if we just put our values in, we've got a 200 ohm resistor and an 8 millihenry inductor. If we put those values in, we get an answer of 25,000 radians per second is our cutoff frequency omega. And that's the answer to that. So part C, redraw the circuit as a potential divider. The reason this question has so many sections is it's meant to help you work through it, so it takes you through the calculation steps. I could have just said, and you'll see in the later questions, I'll say, is it a low or high pass? What's the cutoff frequency? Find the complex voltage transfer function and draw a Bode plot as the frequency changes. This time, because it's the first question, you're being guided through it a bit more step by step. So let's redraw the circuit as a potential divider. Here we go. Simple as that. So what you can see is that V in j omega is applied across both the resistor and the inductor, but the output is taken just across the inductor. And if you can see how we go from this configuration to this configuration, you've got your head around it, and that's really important, and that's really going to help you as you go forward in your studies. So this is how we redraw it as a potential divider. This is all in your lecture notes as well. So hopefully this should make sense. So That's done. Next up, D, calculate the complex voltage transfer function H j omega. So what that means is H j omega is simply equal to the output voltage V out j omega over the input voltage V in j omega. The j omega just represents the fact that it changes as the operating frequency changes. So we can see from this that because it's a potential divider, we can draw this as j omega L over R plus j omega L. So it's similar to our potential divider where we'd have R2 over R1 plus R2. If this was R1 and this was R2, we can just replace that with the complex impedance, because the complex impedance, this j omega L, is also going to be in ohms. So we've converted to reactance or complex impedance down here. So if you work that out, so this is our first step. What we do is we divide it by j omega L because we want to end up with 1 on the top. If we divide through by j omega L, we end up with this expression where we get 1 over 1 minus j omega naught over omega, and that's our complex voltage transfer function. So that's the sort of level of detail I'd expect you to give me in an exam. Don't just write the final answer. I need to see a working as to how you got to that point. So part E says find the amplitude and phase response of the filter at low frequency where omega tends to 0. So what I've done here is I first of all stated what I'm doing. Then we look at the complex voltage transfer function, how that changes when we alter the value of omega. So first up, we're going to replace omega with 0. We change the bit on the top because this is actually 1 at an angle of 0, so I've put that in at this stage already. You can choose to do that a little bit later on if you prefer. And then the bottom part, I've just replaced omega with 0. What happens then is that anything divided by 0 is infinity. So we end up with 1 minus j infinity, which, because this minus j infinity is so much bigger than 1, we can ignore the 1. So we can say that that's equal to minus j infinity, which if we convert to polar form is infinity at an angle of minus 90 degrees because it's minus j direction. So if we just do this phasor division, so 1 over infinity will give us 0, and 0 minus minus 90 degrees will give us a final answer of 0 at an angle of plus 90 degrees. So that's our output, and what we can see from this is that this is the amplitude and this is the phase response. So what I've done here is I've just stated what the answer is. So the amplitude response is 0, which means there's attenuation because anything that comes in is going to be multiplied by 0 before it gets to the output. And the phase response is plus 90, so anything that comes in is going to be phase shifted by plus 90 degrees, which is going to introduce phase distortion. And that's good because we've said it's a high pass filter, so at low frequencies the signal's being strongly attenuated and not allowed to pass through. So next step, now we've done the low frequency, is to look at the high frequency response, and this time we're going to assume that omega tends to infinity. So this is just really running through what we did in the lecture with a specific example. So I've said let's just roll up, at high frequency omega tends to infinity. So every time we see omega in the voltage transfer function, we're going to replace it with infinity. So that's what we've done here. So this becomes our complex voltage transfer function, where it's minus j omega naught over infinity. What we can see is that this becomes, I've converted the top part into polar form already, so it's 1 at an angle of 0 degrees, and for this part, omega naught divided by infinity, anything divided by infinity is equal to 0. So what we have is an answer for the denominator of 1 minus j 0, so that means there's no j. So what we have is just a magnitude of 1, which converts to 1 at an angle of 0 degrees. If you do the phasor division on this, we actually get a final answer of 1 at an angle of 0 degrees. So this is the amplitude and this is the phase response. So let's summarise this. The amplitude response is 1. What that means is the input passes through unattenuated, and the phase response is 0, so there's no phase distortion applied to that signal. So let's move on to part G. We're going to find the amplitude and phase response of the filter at the cutoff frequency, and this is where omega is equal to omega naught. So we're going to do the same procedure, but we're just going to replace omega with omega naught. So that's what we've got here, that's where it comes in. So we end up with 1 over 1 minus j omega naught over omega naught, which of course becomes 1. So for the next step, I've converted the top into polar form, so it's 1 at an angle of 0, and for the bottom part we have 1, which was this 1 from here, minus j1. The next step, which confuses people, is all I've done to go from this part to this part is I've typed in on my calculator and converted it from rectangular form here to polar form here. So the polar form is 1.41 at an angle of minus 45 degrees. And then if you do the phasor division here, so it's 1 divided by 1.41 to get the magnitude, which is 0.707, and 0 minus 45 to get the phase distortion, which gives us an angle of plus 45 degrees. So this is our answer. We separate the magnitude and the phase component, so we can say the amplitude response is 0.707, so there's a small amount of attenuation on that signal. It's not passing through perfectly, and it's the cutoff frequency, so we know this is the part where the behaviour gets a little bit interesting. And the phase response is plus 45 degrees, so there is some distortion. There's a moderate amount of distortion there. So what we're going to do with this now? Now we've got all this information, we're going to plot a straight line Bode plot for the filter. So how have I gone about doing this? Well, there's two separate Bode plots we're going to draw. We're going to draw one for the amplitude, and then we're going to draw one for the phase. So let's deal with the amplitude first of all. We need to know what omega naught is, so we pulled that back from part B of the question. So it's 25,000 radians per second. What you do when you're drawing your straight line Bode plot is you want to plot from high frequency to omega naught as a straight line at 0 dB. Normally, because that's the high frequency gain, because it's a high pass filter, so there's no attenuation. Then when you get to the cutoff frequency, you need to start to roll up the gain of at positive 20 decibels per decade, so that's for every 10 omega as a straight line. So that sounds quite wordy, but we're going to have a look and see how that's plotted in a moment, because I need to rotate the page, so I'm going to talk through the phase part first. So that's how we do the amplitude. For the phase, what we're primarily interested in is just 3 frequency points. At 0.1 omega naught, we can assume that this represents the low frequency phase shift, which we calculated. So we saw that it was positive 90 degrees phase shift at low frequency. And at 10 omega naught, we assume this is the high frequency phase shift, which we calculated as 0. So from 10 omega naught, we assume that it's big enough that it's approximately infinity. And then at omega naught, we just want to check that our phase shift passes through this plus 45 degrees value that we calculated. And at either side of the 0.1 omega naught, we make it a flat line. And at 10 omega naught, we make that a flat line too. So let's have a look at what this looks like. So you'll need your logarithmic paper to do this. Let's rotate that. Okay, so the quality of this isn't perfect. I do apologise. I want it to fit. There we go. So this is the amplitude which we've drawn at the top, and then the phase is drawn at the bottom. So where do we start? I've labelled my graph. I've said this is a Bode plot for a high pass filter, and it's for problem sheet 6 question 1, and this is what the value of our cutoff frequency is. This is important. Next up, I've selected approximately the middle of the graph to be the cutoff frequency, and then at the next decade that's 10 omega naught, and at the next negative decade that's 0.1 omega naught. These are our key frequency points that we're interested in. And then I've labelled my axes, so that's the frequency which is increasing in this direction in radians per second, and I'm plotting the amplitude of hj omega on this scale here. So mark omega naught, which is here, and then the high frequency response is a straight line going all the way up to here. So it's passing high frequencies. That's what this means. What happens here in this section is where it gets interesting. So you start at omega naught, and by 0.1 omega naught you need to be down 20 dB. So that's what you do. And then the next decade you need to be down another 20 dB, which is all I've drawn here. So I drew 2 points and I joined them together. And what this means is that at low frequencies this is attenuated, and the lower the frequency, the more attenuated it's going to be. That's all that this is showing. Next up, for the phase response, I've given my axes labels, so it's phase in degrees. I've plotted plus 90, plus 45 and 0, because these are our really important frequency points. At 0.1 omega naught, I've assumed this is the low frequency the low frequency phase shift, which we calculate as being plus 90 degrees, so I've marked that point there. At 10 omega naught, I've assumed this is the high frequency phase shift, so I've marked that as 0 degrees phase shift, because that's also what we calculated. Then I drew a straight line joining these 2 points together, and I double checked that omega naught was intercepted at approximately plus 45 degrees, which it was. So that leaves you with a sloping line. To finish off the graph, you need to extend backwards at low frequency values and upwards at the high frequency values. So these are flat. This is the transition zone here, and everything outside of it's going to be flat. So what this means is that high frequencies will have, there we go, high frequencies have 0 phase shift applied to them, and low frequencies have plus 90 degrees phase shift applied to them. And that's how you answer question 1.